Hello everyone, welcome back to my channel inphuseclab. Today we're going to talk about LDAP injection. LDAP, which stands for the Lightweight Directory Access Control, is a widely used protocol for accessing and maintaining distributed directory information services over an Internet Protocol network. LDAP enables organizations to manage users centrally, as well as groups and other directory information, often used for authentication and authorization purposes in web and internal applications. The objective of today's room is going to be provide a thorough understanding of LDAP and its role in directory services, explore the LDAP tree structures and its key components, introduce LDAP injection, its impact, and how it can be exploited. Last but not least, we're going to be equipped with the knowledge and skills to identify and mitigate LDAP injection vulnerabilities. A few notes before we start this room. You must have a foundational understanding of how directory services work, particularly LDAP, some basic knowledge of web application security principles and common abilities. We also have to be familiar with the structure of the components of LDAPs, such as the distinguished name, DNs, and the attributes. Alright, let's get started. Structure. In LDAP, directory entries are structured as objects, each adhering to a specific schema that defines the rules and attributes application to the object. This object-oriented approach ensures consistency and governs how objects like users or groups can be represented and manipulated within the directory. Services that can use LDAP. Microsoft Active Directory, a service for Windows domain networks, utilizing LDAP as a part of its underlying protocol suite to manage domain resources. OpenLDAP, an open-source implementation of LDAP, widely used for managing user information and supporting authentication mechanisms across various platforms. LDAP format. LDAP entries can be represented using the LDAP data interchangeable format, a standard plain text data format for representing LDAP directory entries and update operations. LDAP imports and exports directory contents and describes directory modifications such as adding, modifying, or deleting entries. Structure. An LDAP directory follows a hierarchical structure like the file system's tree. The structure comprises various entries representing a unique item such as a user, group, or resource. At the top of the LDAP tree, we find a top-level domain such as DC equals LDAP or the DC equals TryHackMe. Beneath the top-level domain, there may be subdomains or organizational units, such as people, groups, which further categorize the directory entries. Distinguished names serve as a unique identifier for each entry in the directory, specifying the path from the top of the LDAP tree to the entry. For example, we have CN equals John Doe, OU is people, DC is example, and DC is going to be com. Relative distinguished names represent individual levels within the directory hierarchy, such as CN equals John Doe, where CN stands for common name. Attributes define the properties of the directory entries, like mail equals john@example.com for an email address. Search queries. LDAP search queries are fundamental in interacting with the LDAP directories, allowing you to locate and retrieve information stored within the directory. Understanding how to construct these queries is crucial for effectively utilizing LDAP services. An LDAP search query consists of several components, each serving a specific function in a search operation. Base DN, distinguished name. This is the search starting point in the directory tree. Scope defines how deep the search should go from that base DN. It can be one of the following. Base. Search the base DN only. 1. Search the immediate join of the base DN. Sub. Search the base DN and all of its descendants. Filter. A criteria entry must match to be returned in the search results. It uses a specific syntax to define these criteria. Attributes specifies which characteristics of the matching entry should be returned in the search results. The basic syntax of an LDAP search query looks like this. We have the base DN, we have the scope, we have the filter, and then the attributes. Filters and syntax. Filters are the core of LDAP search queries, defining the conditions that entries in the directory must meet to be included in the search results. The syntax for LDAP filters is defined in this document right here, where filters are represented as strings with specific format, such as canonical name equals value. LDAP filters can use a variety of operators to refine search criteria, including equal, equality, presence, greater than, less than. One of the most essential operators in LDAP filters is the wildcard, which signifies a match with any number of characters. This operator is crucial for formulating broad or partial match search conditions. Filter samples. The simple filter, we search for the CN equals John Doe. This filter targets entries with a canonical name CN, exactly matching John Doe, the wildcard. This filter applies the wildcard operator to match any entries where the CN begins with a J. Okay. Complex filters with logical operators. For a more complex search query, filters can be used with each other using logical operators such as and, or, and not. Object class user, and then we have CN John. This filter searches for entries classified as user in the object class with a canonical name starting either with John or Jian. While not commonly exposed directly, LDAP services can be accessible over the network via port 389 for an encrypted or start TLS connection, and 636 for SSL TLS connection. When LDAP services are accessible publicly, tools such as LDAP Search, part of the Open LDAP suite, can be used to interact with the LDAP server. This tool allows the user to query and modify the LDAP directory from the command line, making it a valuable resource for both legitimate administrative tasks and potentially for attackers exploiting LDAP injection vulnerabilities. For example, we can try the LDAP right here. This is a command. This command uses LDAP search to perform a search against an LDAP server located on the vulnerable machine on port 389. Starting at the base DN LDAP or TryHackMe, and using the filter that will search for queries under the organizational unit people. This command uses LDAP search to search against LDAP server located on the vulnerable target machine, port 389 right here, and starting at the base name LDAP.TryHackMe. Using a filter, we search for entries under the organizational unit of people right here. Injection fundamentals. LDAP injection is a critical security vulnerability that occurs when user input is not properly sanitized before being incorporated into the LDAP queries. This oversight allows attackers to manipulate these queries, leading to unauthorized access or manipulations of the LDAP directory data. LDAP injection exploits the way web applications construct LDAP queries, when user input is directly included in the queries without proper validation or encoding. Attackers can inject malicious LDAP statements. This can result in unauthorized access to sensitive information, modifications of directory data, or bypassing authentication mechanisms. The process is analogous to SQL injection, where malicious SQL statements are injected into the queries to manipulate database operations. In LDAP injection, the malicious code targets LDAP queries instead. There are some common attack vectors. Authentication bypass, modifying LDAP authentication queries to log in as another user without knowing the password. Unauthorized data access, altering LDAP search query to retrieve sensitive information not intended for attackers' access. Data manipulation, injecting queries that modify the LDAP directory, such as adding or modifying user attributes. Injection process. Making an LDAP injection attack involves several key steps, from identifying the injection point to successfully exploiting the vulnerability. Injection process. Making an LDAP injection attack involves several key steps, from identifying the injection point to successfully exploiting the vulnerability. This diagram illustrates the interactions between the attacker, the web applications, and the LDAP server using the LDAP injection. The attacker submits a malicious input to the web application login form, which constructs an LDAP query incorporating this input. The LDAP server then executes the outer query, leading to potential unauthorized access or information disclosure, depending on the nature of the injected payload. The attacker, web application, and LDAP, they submit a malicious input. Here, username equals something else like this, and this payload will be constructed with the LDAP query, which changes the behavior of the LDAP directory. The query execution results and returns the entry that starts with the letter F, and then it returns to the attackers. That's similar to SQL injection. Exploiting LDAP. LDAP injection can be particularly dangerous when exploited within authentication mechanisms. Attackers can manipulate LDAP queries for user authentication to bypass security controls, gaining unauthorized access to the applications. For example, below a simplified PHP code snippet used in the web application user authentication against the LDAP server. This code is vulnerable because it directly inserts user supply input, username, and password into the LDAP query without proper sanitizations or escaping. An attacker can exploit this to inject malicious LDAP filters. To exploit this vulnerability, an attacker can submit a username with a malicious LDAP filter. For example, the attacker could use a username like the asterisk, which, when inserted into the LDAP query, effectively turns the query into the condition that always evaluates to true, bypassing authentication. This query will authenticate successfully if there is any user in the LDAP directory, as the injected condition UID equals asterisk will always be evaluated to be true. Authentication bypass techniques. Tautology-based injection. Tautology-based injection involves inserting conditions into an LDAP query that are inherently true, thus ensuring the query always returns a positive result, irrespective of the intended logic. This method is particularly effective against LDAP queries constructed with user input that is not sanitized. For example, consider an LDAP authentication query where the username and password are inserted directly from the user input, which is this one, UID user input, user password. An attacker could provide a tautology-based input, such as these operators for user input and PWD for password input, which transform the query into. From this, we modify the payload. This one will go in here. This query effectively bypasses password checking due to how logical operators are used within the filter. The query consists of two parts, combining using an AND operator. This one specifies any entry with a UID attribute, essentially all users because the wildcard matches any value. So basically you retrieve all the user that has a UID. This one, the OR operation. The OR operator, meaning that any of the two conditions enclosed needs to be true for the filter to pass. So we have two conditions, this one and user password PWD. In LDAP, an empty AND condition is always considered true, and the other condition checks if the user password attribute matches the value PWD, which can fail if the user is not using the PW as that password. Putting it all together, the second part of the filter will always be evaluated as true because of the AND condition. The OR operator only needs one of its enclosed conditions to be true, and since AND is always true, the entire OR condition is true regardless of whether the user password is true or false. Therefore, this results in a successful query return for any user without verifying the correct password, bypassing the password checking mechanism. The wildcard injection. Wildcards are used in LDAP queries to match any sequence of characters, making them powerful tools for broad searches. However, when user input contain wildcards is not correctly sanitized, it can lead to unintended query search results, such as bypassing authentication by matching multiple or all entries. For example, if the search query looks like this is N, and then we have the first condition, the second condition right here, UID. An attacker may use a wildcard as an input for both UID and user password. Using an asterisk for user input could force a query to ignore specific usernames and focus instead on the password. However, since the wildcard is also present in the password input, it does not validate the content of the password field against a specific expected value. Instead, it will only check for the presence of the user password attribute regardless of its content. This means that the query will return a positive match for any user without verifying that the password is provided during authentication matches the stored password. As a result, this effectively bypasses the password checking mechanism. Authentication bypass examples. To demonstrate this one, we go to this website. Now, before we go to the website, I have already added this IP address to the host file. As you can see it right here. I always do that because I don't want to keep retyping the IP address, and then I don't want to remember the IP address of the target machine. It changes every time. Remembering LDAP.TryHackMe is much easier. Right here we have exploiting LDAP. Based on the code above, the application constructs an LDAP query for authentication based on the user input with a proper sanitization. An attacker can exploit this by submitting a username and password with a character application not anticipated, such as an asterisk for the UID and user password attribute value. This makes the conditions always evaluate to true, effectively bypassing password checking. In this case, just an asterisk, same thing here. And we should welcome Bob Smith. This injection always makes the LDAP query's condition true. However, using just the asterisk will always fetch the first result of the query. To target the data beginning in a specific character, an attacker can use a payload like the F and an asterisk, which searches for UID that begins with the letter F. F. Welcome, TryHackMe. There's no exclamation mark. Blind LDAP injection is a more subtle variant of LDAP injection, where the attacker doesn't receive direct output from the injected payload. Instead, they must infer information based on the application's behavior. This type of attack is more challenging, but can still be used to extract sensitive information from an LDAP directory. The blind LDAP injection requires a different approach due to the lack of explicit query results. Attackers must rely on indirect signs, such as changes in the application behavior, error messages, or response timings, to deduce the structure of LDAP query and the existence of the vulnerabilities. For example, below is a code snippet that uses LDAP query to check for existence of a user but only returns a generic error message at failure. The application also checks if the submitted email is the same as the email in database. This code is vulnerable to blind LDAP injection because it constructs an LDAP filter using unsanitized user input. However, it only provides vague feedback, making it challenging to exploit directly. To exploit this vulnerability, an attacker can use a technique known as Boolean-based blind LDAP injection. To exploit this vulnerability, an attacker can use a technique known as Boolean-based blind LDAP injection. The attacker injects conditions into the user field to make the LDAP query true or false. observing the application's behavior to infer information. For example, an attacker might try injecting a username with this payload right here, which then included in the LDAP query checks for any user start with A in the UID. So this is the URL encoded version of this payload right here. They are the same. So we have to copy this one. If the application returns something wrong in your password, the attacker can infer that the user with an account that starts with an A in their UID exists in the LDAP directory. To check for the next character, an attacker can reiterate the payload with the next character, for example, A, B, OK, and we continue until we fully extract the username. We can use burp intruder to do it. If we get a password incorrect, it indicates that the next character is not B. An attacker can automate this kind of check by iteratively guessing the characters of the email by observing the web application's behavior in response to grab input, similar to Boolean-based SQL injection. Techniques for extracting information. Boolean-based exploitation. This involves injecting conditions that are evaluated to be true or false. Boolean exploitation. This involves injecting conditions that are evaluated to be true or false and observing the application's response to infer data. For example, if the application behaves differently when the condition is true, the attacker can deduce that the injected condition matches the existing entry of the LDAP directory. Error-based inference. In some cases, specific injections might trigger error message or peculiar application behavior, providing clues about the LDAP structure or confirming the success of particular payloads. Automating the exploitation. To automate the exfiltration of data in the previous task, you can use a Python script right here. For the breakdown of the script, first the import. Let me put it here. We import request, beautiful soups, string, and temp. Request is a Python library for making HTTP requests. Beautiful soups from BS4 is a library for parsing HTML documents, making it easier to navigate and search the parse tree. String is a module containing common string operations, including a collection of string constants. Temp, a module providing various temp-related functions. Setup. The URL is going to be the URL of the target machine. The char set right here includes lowercase, uppercase letters, digits, and special characters. This set represents all characters in the script will iterate over the guest password. Variable initialization. Successful response file is a flag used to control the while loop. It starts as true to enter the loop and is set as false when no successful character is found. Successful cars start a sequence of successfully guessed characters. HTTP headers. A dictionary headers is defined to the content tab to set the application to HTTP headers. A dictionary headers is defined with a content tab set to application/x www from user encoded. indicating the body format of the HTTP post request. Where's header? This is the headers right here. The main loop. This is the script, the loop where the script enters a while loop. Main loop. The script enters a while loop that continues as long as the successful response found is true. Inside this loop, it iterates over each character in the car sets. Crafting and sending HTTP requests. For each character, the script create a dictionary data with a key value pair. Crafting and sending HTTP request, which is where is it? Trying password character adjusting. Data equals username suspects. Crafting and sending HTTP requests. For each character, the script creates a dictionary data. Where is it? Data. Right here. With a key value pair intended for the HTTP post request. The username field is injected with a payload combining successfully found characters and the current character being tested, followed by these operators, which is part of the injection syntax. The password field is arbitrarily set to PWD. So in this case, the password doesn't matter. An HTTP post request is sent to the target URL with the crafted data and headers. This is when we send the post request. Response handling. The response content is parsed with a beautiful soup to analyze the HTML structure. The script looks for the p tags with a style attribute color green. This is which is assumed to indicate a successful guess. Number 8. Characters verification. If such paragraphs are found, it means that the current character is part of the password. This character is then appended to the successful cards. Right here. These are the code right here. If the successful response found, then the successful character is added. If no paragraphs meet the criteria, the script concludes that no successful characters were found in the current iteration, prints a message, and exits the loop. Output. Once all the characters have been tested or the correct sequence is found, the script prints the final sequence of successfully found characters. The above script iteratively guesses the characters of the email by observing the web application's behavior in response to a crafted input. So we can modify the script a little bit. Right here we can do LDAP.TryHackMe. We create a script and we run it. We have successfully enumerated the username and password. Username is admin, password is blind. Blind at LDAP TryHackMe admin. Blind at LDAP TryHackMe. Brute force as below. Use the payload to log in. Make sure to use the asterisk as password. Hello admin, so we log in with the blind LDAP TryHackMe. What is this for? That's the whole string. Admin underscore line at LDAP.TryHackMe. Wait a minute. We've got admin bl1nd at LDAP.TryHackMe asterisk then an asterisk. Hello admin user. Found out successfully. This is the normal one. This should be admin at line LDAP.TryHackMe. I'm flat, but where's the final payload is login. Make sure to use the password. Oh, this is blind. We have to use the login page. Interesting. Alright, so that's it for the room today. It's pretty short and easy to understand. There's nothing much going on. The vulnerability is similar to SQL injection, but the syntax is a little bit different and it makes it take some time to get used to it. So when it comes to protecting your applications against LDAP injection, there are also things to keep in mind. If possible, applications should avoid using copying user-controllable data into LDAP queries. If this is unavoidable, then the data should be strictly validated to prevent the LDAP injection. And of course, because we depend on the user input, the user input has to be sanitized first before being processed by the LDAP query. And at a minimum, the input containing any LDAP meta character should be blacklisted. No special characters like the parentheses, asterisk, columns, semicolons, single quotation mark or double quotation marks, etc. They should be whitelisted. They should be blacklisted. I'm sorry. Alright, so that's it for today's video. If you have any questions, feel free to reach out to me. And thank you very much. Until next time. Bye.